will be available to you afterwards. So just remember that. A few ground rules. I'm going to be lecturing the best I can. We'll see how it goes. And I bought myself a screen here, and the screen lets me write on PowerPoint, so I can write equations, because this is going to be very, very interesting course with a few equations. And I guess the ground rules is I would like you to leave your cameras on, because I like to see your expressions. So, you know, I would just prefer to do that. It's more like a live audience as opposed to a dead, non-existent audience. And if you at any time have questions concerning the material that I present, feel free to go off mute and go ahead and dive in and ask me the questions, and we'll do the best we can. I'll do the best I can with being clear, and we'll see how that goes. So with that, I'm going to share my screen.
Dr. Marks?
Yeah.
So are you going to be sharing the lecture recordings after each lecture?
Yes.
So if we like weren't able to attend one day or something, then would we also be able to?
My philosophy is the only thing that you are responsible for is the examinations that we have. So there's no requirement. If you think you can learn it all from the book, which I don't think you can, you're welcome to try. So no, there's no requirement. So, and if you do miss a lecture, you'll be noticed, because we only have 6 people, and it will hurt my feelings, but not for long. Okay. Okay. Appreciate it. Okay. So let me share my screen here. And I sent everybody some email already. And in that email was some important stuff. See if I can find it. Let's see, where to go. Can you see my screen? Okay, okay. See the importance of me seeing you is that I can get your response here. Okay, here we go. I think this is it. I had this all up and running. This was going to be a seamless presentation, but you see my seamlessness kind of jumped the gun here. So where is my, oh, there it is. Oh, it's right here. Shoot. Okay, I emailed everybody a copy of this. I emailed everybody a copy of this list here. And this list is going to be on Google Sheets, and I shared with you the information. So I thought, instead of, just sharing piecemeal all of the links in the course, I would just share this single document, and it would have all of the links that were required for the course to help you do great and wonderful things in the course. So here is the Zoom address. This is my home Zoom address, so it's not going to change every time. Thank you, Glauco, for pointing out how to do that. And there's also going to be homework on Google Docs. And I will also give you homework in the book. Now, the book, let's see, I think I have the book here. Let's see if I can reach it without hurting myself. This is the text. It's a book I wrote, and you can see it's really thick, right? So it makes a good doorstop also if you want a hard copy. So we're going to be using this book, and there's also lots of assignments in this book that have answers posted right in the book. So I'm going to be suggesting those, but I don't think those are going to be very very learning appropriate. So I'm going to give you some other homework, and I'm going to list this also in Google Docs, and it's going to be here. So you can see 53, 51 homework, and I'll assign this by number. And then we'll decide how we do with this. One of the challenges that we have, because we don't have easy class participation, is for me to make sure that you're engaged. And we want to make sure that you're engaged in a number of ways. One is, first of all, if you have any questions, occasionally I will pose a question and invite a response. If anybody wants to go off mute and talk about it, we'll be happy to do that. And so, yeah, we're going to have to do some sort of collection of the homework. So be prepared to make a good effort at presenting the homework solutions that you do. I will give the homework. I will give the homework problems, and you will present them. And maybe the easiest way is just take a clean, and please make it clean, a clean photograph with your cell phone, and you can get it to me. I'll supply a document in Baylor's box where you can deposit the solutions that I can look at. Is that okay? So I think you all have that. If I don't know if you ever want to invest in a scanner, Amazon's got some pretty decent ones for, I don't know, about $100 or so, but I don't think that that's necessary. So our class
Dr.
meets,
Marks?
yes.
So you're saying homework is not going to be like you usually do it, where we, go up to the board and answer, and we're going to actually be turning it in?
I haven't decided. I think that I might do that also. I might do a combination of the two.
Okay.
So I will announce that as we go on. Yeah, that's my favorite way of doing it, which is to assign homework and then to select students at random to present the homework solutions. And we might do that too. So I haven't made my mind up totally on doing that. Okay, homework on Google Docs. Here's the Amazon place where you can get my book, bestseller. And you'll notice that on Amazon, the cost of the book is really high, but if you look how thick it is, the cost per page isn't that much. So you should be happy with that. I'm also going to be doing a lot of presenting with slides. Unfortunately, presenting with slides is not the best way to present material. I at one time had a class in stochastic processes and probability, and I thought I'm going to make my class all slides. So I made my class all slides, and I presented the slides, and all of my teaching ratings just went. It just wasn't good. There's a tendency for the professor to go too fast through the slides. And so I'm going to try a hybrid of this. I'll be presenting the slides, and I'm going to be documenting it with my little tablet here as best I can. This isn't the perfect way to do it, but I think we can get by with it, and hopefully with your patience, we can do great and wonderful things there. The office hours are, I think, probably the best thing to do is have office hours after class. I will hang around, and then if anybody wants to stick around and ask questions concerning the homework or the material, that would be a good time to do that. And we will be able to perform that office hour task over Zoom. Okay, any questions at all? Okay, probably the way I do examinations is orally. I think that probably a midterm oral, and a couple of you have had me. I think both Glauco and Adam have had me. And it sounds terrifying to have oral examinations, but really the horror of having an oral examination is a lot worse than having it. So have any of you guys heard about, what is it? Is it Craig or Clegg or something like that? The cheating site? Nobody's heard about that, huh?
Chegg?
We had a big, what's that?
Chegg?
Say again.
Chegg.
Chegg. Okay, yes, Chegg. We had a conference talk about this during the faculty meeting, and I guess this is going crazy, where people take homework and they submit it to Chegg, and they get a response. And sometimes this can be done truly in the course of a examination, so people can take a picture of the problem and send it in, and they get an answer because they got full-time people that pay pretty well. And if you're in a developing country, the pay that they give is really, really good. And so this is a big challenge. I don't think that that'll be a problem here, but I also think that oral exams get around this problem, because I don't see anybody doing that. And in the examinations that I'll give you, I'm primarily interested in how much you understand things. I'm not interested in the memorization of equations, but in the actual accumulation of understanding that you have. Glauco, Adam, you've both had me for oral exams. Do you have any comments on the oral exams? They weren't that bad, were they?
No, yeah, I was scared going into the first one, but no, it was fine. They're usually pretty fun, even.
Yeah, we have a good time. If it's gone good, we tell jokes and things of that sort. So okay, so yeah, the slides are in box, and I'm hoping that you have access to the slides at this address, and you have download capabilities. I'm going to make a number of different elements of slides, and you're going to be able to see them as we go along. Okay, any questions about the foundations at all? Okay, hearing none, let's go on to the presentation. Well, first of all, talk about the historical foundation. I find it just fascinating to look at the history of people whose names we hear. For example, like Fourier. Everybody hears about Fourier. They kind of know what he does. In fact, most people don't know what he does, just that he has something to do with Fourier. But it's fun to look at him historically. So I wanted to talk about Fourier historically. One of the things we're going to do in this course is first have an adult review of Fourier analysis. This is stuff that you learned as an undergraduate, but we're going to be presenting it at a much higher level. And at this higher level, you're going to see, hopefully, a lot of interesting ideas and rules for playing with Fourier analysis, ways of thinking. Lord Kelvin famously said that Fourier is like a mathematical poem, and I really believe that. I think that if you get into the Fourier analysis and you get the intuitive understanding of what is going on, there's a real inherent beauty associated with it. Fourier analysis is associated with millions of things, and no matter what you do in electrical engineering, you're going to talk about Fourier at some time. You've already probably talked about Fourier. Fourier is ubiquitous. It occurs all over the place. In fact, it occurs in nature. Do you know that free space does a Fourier transform? If you've taken a course in optics and you put an aperture here, say a square aperture, and you illuminate it like with a laser, if you go out in the far field is the Fourier transform of the aperture, and that is performed naturally in free space. So we're used to thinking of Fourier analysis in terms of time signal into a frequency signal, but it is ubiquitous. And I would say probably it's only second to the differential equation as the most studied field in mathematics, at least for applied mathematics. So with that, let's go to the first slide. Here's the book again, by me, great book. And here's Jean-Baptiste Fourier. He was kind of a chubby guy, apparently, and his name was Jean-Baptiste Joseph Fourier. Of course, the Jean-Baptiste was what? Named after John the Baptist in Scripture, the guy who was the prophet for Christ and got beheaded by Herodotus or something like that. And he studied for the ministry for a while, but he really liked math. And he presented his famous thesis in December 1807. It's fun to put these things in history. And it was on the propagation of heat in solid bodies. It does turn out the Fourier analysis is applicable anywhere where you have linear differential equations, from a vibrating string to heat to a vibrating air column. All of these beg for Fourier analysis. So he was interested in waves in heat in solid bodies and decomposed his analysis into the idea of a Fourier series. Now, talk about being inhibited. You know, a lot of you are inhibited by your PhD committees. You're all going to be taking master's defense or PhD defense or PhD dissertation defense. Here was Fourier's PhD committee. It included Laplace. Everybody has heard of Laplace, one of the greatest mathematicians of the era. And Laplace, we all know Laplace because of the Laplace transform. We know Laplace because of the Laplacian in electromagnetics. We have the Laplace distribution in probability. So Laplace was all over the place. He was just a genius of a mathematician. Also on his committee was Lagrange. You've probably heard of Lagrange from Lagrange multipliers. Lagrange was also a prolific mathematician. And then there were two other less known mathematicians that were on Fourier's committee, Monge and Lacroix. Lacroix, of course, went on to find the bottling company that sold carbonated water. That's a joke, by the way. He didn't go on. That was just a coincidence. You're familiar with LaCroix water, right? Okay, so no, he had nothing to do with carbonated water. Maybe one of his ancestors did, though, right? Maybe one of his ancestors started the carbonated water. But this was the examining committee, so you talk about being intimidated. The interesting thing is that both Laplace and Lagrange had doubts about Fourier's work. And here was their doubt. Let's see if I can get this pin to work. Okay, where's the pin? Oh, there it is. Okay, here was their problem. They said, you know, what Fourier says is that we can have a periodic signal that, what's wrong? Okay, we can have a periodic signal such as a periodically repeating square wave. So we have this signal, and this is our x of t, if you will. Okay, I'm going to get this down, guys. It's going to take me a little while. But we have this repeating signal with this square wave. And both Laplace and Lagrange said, look, Fourier, how the heck do you ever expect to get this incredible discontinuity here, this continuity that goes straight up, by fitting it with things that look like smooth sinusoids? You have a smooth sinusoid and you add them up, those smooth sinusoids are going to add up to something smooth. And how are you ever going to get a sharp edge? So they were very hesitant about accepting Fourier's thesis, but indeed they ended up doing it. And as we'll see, there was a modicum of truth in their objection. These guys were very, very bright and understood some of the challenges of the Fourier series. But the other thing which is surprising about Fourier is that he did incredible things otherwise. He was under the role of Napoleon. My phone is ringing. And I can't put it on hold. He was sent to Egypt, I believe, by Napoleon, and was one of the first, if the not first, Egyptologist. He looked at the ruins of Egypt and began to map out the history of Egypt based on the ruins that were in Egypt at the time. He also wondered why it was the Earth kept all the heat inside. And he hypothesized that there was this reason, this layer in the atmosphere that trapped the heat within the body of the Earth and kept the world warm. And of course, we know this today as the greenhouse effect, and Fourier was one of the first to recognize this. He was made a baron by Napoleon. So he was able to talk about royalty. But of course, these things don't live on, and he is primarily known for his work in the Fourier analysis and the things which are in the field of Fourier transforms. So this is, I think, fascinating stuff. Here are some of the things that I've listed in the book that bear Fourier's name. I mean, it's incredible. Fourier series, Fourier transform, Fourier analysis, Fourier theory, Fourier integral, Fourier inversion, Fourier descriptors. You can read the rest. There's Fourier spectroscopy, which is a type of spectroscopy which is based upon the Fourier transform. And there's also Fourier transform nuclear magnetic resonance for those of you in biomedical engineering. There's Fourier vision, Fourier optics, and Fourier acoustics. I skipped Fourier spectroscopy. I like Fourier spectroscopy because spectroscopy is one of the most fun words you can say in the English language, spectroscopy, and Fourier spectrometry. So this is just an incomplete list of some of the things that Fourier's name is associated with. So you can see that the impact that he has had has been incredible. So we're going to deal with Fourier's theory. We're going to first of all deal with it in one dimension in a review sort of sense to establish notation and the trajectory of where we're going. And then we're going to extend it into higher dimensions because a lot of multidimensional signal analysis is based on Fourier's theory. In fact, you're familiar with JPEG coding, right? You've heard of JPEG images. JPEG images are based on Fourier transforms, actually using a cosine kernel instead of an e to the j. But nevertheless, they are based on Fourier analysis. And we'll look at a lot of the applications. One of the things I'm very interested in here is to, first of all, to establish a base of understanding of Fourier. Once we get this understanding of the base, we're able to build on it. I am a person that really enjoys reduction to practice But in order to get to reduction to practice and applications, we're going to have to establish a firm foundation for Fourier analysis and ways of thinking about signals before we dig deep into some of the applications. And we'll show applications in a number of places: image deblurring, subpixel resolution. We'll talk about tomography. Tomography is the reconstruction of images from their projections. And we'll talk, all of these are based on Fourier analysis. So that's where we're going. Okay. So let me go now to the second chapter. The second chapter is kind of a review of signal analysis. This many of you have had. Some of you, I think that the Baylor course, the undergraduate course, is 33-35, where you begin to talk about Fourier analysis. And we're going to review this quickly and succinctly, and once you get done with it and the homework and such that I'll give you, you're going to, I think, enjoy it a lot, enjoy Fourier analysis a lot more and have a deeper understanding. I've had people come out of this course and say the thing that they enjoyed most is they didn't have a complete appreciation of the Fourier transform, and you will have an appreciation after going through this boot camp of the Fourier analysis. So here's what we're going to talk about. This is from the chapter. Now, there are certain things that we are not going to talk about. So, okay, where'd my cursor go? There's a cursor. So we're going to talk, we just talked about the introduction. We will talk about signal classes and the Fourier transform and all of the elements under the Fourier transform. One of the things that we're not going to talk about is the relationship between the Fourier and Laplace transform. If you want to read that, you can read that. It's very interesting. You're familiar with the Laplace transform, and some people say just take the S and replace it by a j omega and you have a Fourier transform. If you remember that, if you don't remember that, don't worry about it. But no, it's not simple as that. There's a little bit more, but because of time, we're not going to be able to go through that. The other thing that we will cover is continuous Fourier transforms. We will look at the theorems associated with Fourier transforms. This will give you an idea of how to manipulate the Fourier transform. You can see here listed are some of them. They might ring a bell to you: the derivative theorem, convolution theorem, inversion theorem, duality theorem, and the scaling theorem are all theorems which are in Fourier analysis. When we get to higher dimensions, we'll find out that there's some other interesting theorems which are applicable in higher dimensions that don't manifest themselves in one dimension. And so that's going to be coming up when we talk about the Fourier analysis in higher dimensions. We will talk about some continuous Fourier transforms. One of the things that we're going to do is establish notation. One of the problems that people have in applying Fourier analysis is all of the little details. Details like, you've seen them, the forward transform is one way. If you do the inverse Fourier transform, you get a 1/2 pi in front. You might or might not remember that. But all that bookkeeping, trying to keeping where all those 2 pi's are really crazy. The other nitpick that I have is that most Fourier analysis deals with radial frequencies. And I don't know about you, somebody comes and tells me there's something vibrating at 100 radians per second, which is, what do we call that? There I am, okay. I lose my cursor here. We usually think of omega, right? We usually think of omega, and this is 100 radians per second. What does that mean? I have no idea what that means. Do you have any intuitive idea what that means? Usually you divide by 2 pi. So you get a 2 pi times u, where u is what we're going to use as regular frequency. It's going to be in cycles per second. And we'll find out that the Fourier analysis becomes a lot simpler when we talk about real frequency, cycles per second, as opposed to talking about omega, radian frequencies. We'll talk about some great functions, some of my favorite functions: the Dirac delta, a little bit of trig functions, sync and related functions, the rectangle function. All of these are things which we're going to cover. The signum function, these are pretty simple. We're familiar with the Gaussian function. Maybe you haven't seen this one before, but this is something called the comb function. The comb function is called the comb function because, as we'll see, it looks like a comb, and it's kind of cool. We'll deal with the triangle function, the array function. Now, if you're involved in phased arrays, the array function is very important, because typically what you get if you have a sequence of a finite number of point sources, the Fourier transform of the far field is the array function. So the array function is very useful in such analysis. We'll deal with the gamma function, and not on here is we will not deal with the beta function. Beta function is beyond the sort of stuff that we want to do in this course. But the gamma function is important, because the gamma function is important in the area of what we see here at the top, which is the Bessel function. The Bessel functions are ubiquitous in multidimensional Fourier transforms, and we see them all the time. Not as frequent as sinusoids, but Bessel functions occur all the time. If you've ever watched a drum head vibrating, chances are the drum head's vibrating in a Bessel function. I used to get styrofoam cups with coffee. I don't know, has anybody ever done this? And you drag it off the table and there's a little bit of friction, and you see on top all these concentric circles on top of the coffee. Has anybody done that except for me? Okay, I see no responses. Okay, maybe when we get together sometimes I can show you my Bessel function of my coffee. But you drag this coffee across and you get this resonance on top of the coffee. It looks like a number of concentric circles, and that is literally a Bessel function. And so Bessel functions are pretty ubiquitous. If you deal in electromagnetics with circular waveguides, your modes of propagation are Bessel functions. So Bessel functions are worth our study and our time. We are not going to get deeply into Bessel functions, only enough to do the higher Fourier analysis sort of work. We will do something called the sine integral, which is very simple, and we will not deal with orthogonal polynomials. There's a whole chapter on that, and I think that's above and beyond what we want to touch on. Other properties of the Fourier transform, yes, we will deal with these, and yes, all of these, the signal prop, the conjugate symmetry. Now, looking at these, probably you won't understand a lot of these. Probably not the Hilbert transform. Hilbert transform is a fascinating result, but I think we need to skip it. And the related thing of the Hilbert transform relationship with causal signal spectrum. We'll deal with the power theorem, definitely. And the Poisson sum formula, very important, powerful theorem in Fourier analysis. The area of orthogonal basis functions is something that we will totally skip in this course in chapter 2, so we won't go into that. We will go into the discrete Fourier transform, as you see here in 2.5, and its relationship of the DFT to the continuous time Fourier transform. That's what we want, right? Usually when we do a DFT, and a DFT, by the way, is implemented in code as a FFT, of course. When we do an FFT or a DFT, what we're trying to do is compute the Fourier transform, and it has to have some relation to the continuous time Fourier transform if we're dealing with things in the real world, because most of the Fourier transforms that we come across are analog in nature. And we have digital computing, we have this analog phenomenon, and we need to look at it. So we'll look at the discrete Fourier transform. We'll look at circular convolution. Again, you might remember circular convolution from the undergraduate course. If not, you'll know it now. And I'm not sure we'll talk about DFT leakage. We'll see if that is important when we get there. We will not be talking about related transforms. Unfortunately, we don't have the time to do that. And so this is going to be the contents of chapter 2. So I look at this, what I've done, and it looks like one big mess, but this is what I get using this pen and this little tablet. So that's the material that we're going to cover in chapter 2. We're also going to cover a later chapter of multidimensional signal analysis, where we'll extend some of these ideas to higher dimensions. Some are straightforward generalizations of the 1D counterparts, and there are other things which are not straightforward extensions, and those are going to be the most interesting. We will talk about the sampling theorem, and then the sampling theorem in higher dimensions, and that's interesting too. so that's something which is going to come up. I posted something. This is very interesting. You know, at COVID, you are supposed to space yourself 6 feet from everybody, right? So if you are in a room which is packed, what is the geometry that you should situate yourself in to get the most people in the room and still allow social distancing? Anybody have any idea?
Hexagonal.
Yes, that's exactly right. Yeah, that's for David's exactly right. It is hexagonal. Where's my cursor? I keep losing my cursor. Yeah, if you this is not a perfect hexagon, but you'll notice that this is the way where you maximize the people that you are getting in the room, and each one of these can be 6 feet, and you get the most people per unit area if you pack them this way. There's a couple of interesting things in that this same sampling geometry is often optimal in sampling images. We don't use it because rectangular is more convenient, but hexagonal is many times the way to go for sampling images. You'll also notice that there's a crude idea of multidimensional periodicity here. We usually think of periodicity maybe being rectangular, spreading things down and spreading them to the right. But no, that's not the case here. We do not have a rectangular periodicity. We have a hexagonal periodicity, which is something that manifests itself in higher dimensions. So that's a little tease of some of the things that we're going to. So let's get in. Oh, by the way, after we get done with multidimensional sampling theory, multidimensional Fourier analysis, we will go into what I think is one of the most fascinating areas in analysis, which is called POX, alternating projection onto convex sets. And I will show you alternating projection onto convex sets and its applications in a plethora of areas, from tomography to image deblurring to actually now my mind's drawing a blank. Just take my word for it. There's lots of applications, and we're gonna see these applications when we get there. Okay, so let's first of all talk about signal classes. We talk about signals, but it's going to be interesting to talk about signal classes also. And look at this. This is I was doing this with my practice, and isn't that interesting? I didn't mean for that to stay. Okay, well, it stayed, so I'll go ahead and use it. Here's the definition of a periodic signal. The definition of a periodic signal is x of t is equal to x of t minus t. Okay, I found out that if I push the wrong button on this pen, it erases everything, so I have to be very careful. X of t is equal to x of t minus t. Big T is the period, which means if you take this x of t and you move it over one period, so you take this function and you shift it over one period, you get exactly the same thing. And this has to be true for all values of t. The upside down A means for all values. That's what they teach you in mathematics. So this has to be true for all values of t. And we have a similar relationship for discrete time signals. Before discrete time signals, notice that the definition of period is not unique. We could literally go this far, couldn't we? In other words, 2 periods, and we could say we could replicate it this far also. So this has a period of t. It also has a period of 2t. Typically what we do is that we take these and choose the smallest value of t, which is applicable. So with this in mind, we have the definition in discrete time. Now you'll notice the difference in discrete time. You notice we have the square brackets here. We will always use the square brackets when we're talking about discrete time. That way there's no confusion where they're talking about discrete time or continuous time. And we will use the parentheses up here for when we're talking about continuous time. And so this gets away the different ambiguities. And of course, if we have a sequence that replicates itself, like this. And I'm having a problem drawing straight lines today, aren't I? Okay, these are supposed to be 2 periods. So here is a period, and here n is equal to 3. That's the period that we have. And this is n, and this is x of n. And we can see that we have a periodicity here. So with this, let me ask you a question and see if I get a response here. Suppose we have the function x of t is equal to 7. And this down here, of course, is t. Some of the most interesting problems come from degenerate cases. This is a pretty simple case. And the question is x of t equal to 7 periodic?
I would think it is periodic with an infinitesimal period.
Yes, in fact, the period can be anything that you want here. It doesn't matter what you're doing. The period can be infinitesimal. You can flip this over any element of t, you can shift it over any value of t, and we get exactly the same thing, don't we? We get exactly the same thing. Keeping with the convention of using the smallest value, we would probably say that this has a frequency of t is equal to 0, right? This is consistent with up here. We typically talk about the frequency as being 1 over the period. So if we have t is equal to 1 second, then the frequency is 1 cycle per second. Down here, the frequency would be what?
Infinite.
Yeah, that doesn't sound right, does it? Yeah, that doesn't sound right. So, but if we keep with our convention, that's what we get here. But indeed, this is periodic. Why is it periodic? It's periodic by definition. We have defined periodicity up here. And this is the definition of periodicity. This equation fits the definition of periodicity. Therefore, it's periodic. And you can choose the value of t that you want. So this is the idea of periodic signals. Finite energy signals. Here we have something interesting also. Let me tell you why we call it energy. This is a course in electrical engineering, so we better draw a circuit element here. That's my attempt at a resistor, a 1 ohm resistor. Is that okay? And coming into this 1 ohm resistor is a current, and this current is x of t. What is the power as a function of time which is dissipated by that resistor? If you remember, twinkle, twinkle, little star, power equals I squared R, right? So the power which is associated with this as a function of time is x of t squared. It's equal to the current squared. That's very simple. So the question is how much energy is dissipated by this resistor over an interval of time, let's say of all time. The energy which is dissipated by the resistor is equal to the integral, the area under the curve of the power as a function of time, right? And that, of course, is equal to the integral in our analysis of x of t squared. Now, we use the absolute value in case the x of t is a complex signal. So we see that the energy here in watts on a 1 ohm resistor case is equal to the area under the magnitude squared of the function, and that's what we call this function here. I'm really not liking not being able to see my cursor here. So therefore, if this is infinite, we say that we have a finite energy. I'm sorry, if it's less than infinity, we say we have a finite energy signal, which is kind of good. So take, for example, an x of t equal to e to the minus t over 2. And we're going to multiply this by a mu, and our notation for a unit step, this is going to be our unit step. Everybody's familiar with the unit step function. So this function looks like, where'd my cursor go? There you are. I might have to change the background to black so I can see it. I can see it in the green. Can you see my cursor in the green? But I get it over here and it just kind of goes away. Okay. So this looks like this, right? Not as wiggly as I drew it, but it looks like what? It looks like a capacitor discharging, right? E to the minus t. So okay, I'm gonna get better here. X of t squared is equal to e to the minus t times a unit step. And the energy is equal to the integral over all time. By the way, for convenience, sometimes I'll just use the integral over all time instead of from minus infinity to infinity. These are equivalent notations. So the integral over all time of e to the minus t, mu of t, we know is the same thing, and this is pretty simple stuff. It's the same thing as the integral from 0 to infinity of e to the minus t dt, because this unit step blocks out everything from minus infinity to 0. And if you put the calculus to it, that turns out to be 1. So that's less than infinity. So therefore, we have a finite energy signal. So this is a finite energy signal. So this is one example. Here's another example. Maybe I should put finite energy here. Here's another example. Suppose that we had x of t. This is rough. I'm starting to get writer's cramps. Give me a second to get the blood back in there. X of t is equal to the cosine of t. Here we have, oh, see, I pushed the wrong buttons and everything disappeared. So that's okay. I have a clean slate from which to work to try to redeem myself. X of t is equal to the cosine of t. We all know what this x of t looks like, don't we? This x of t looks like this. Of course, it looks better than this, but I hope you get the idea. And if we don't look at the square of it, it looks like this. Looks like a cosine writing on a bias. Is that okay? Now, what we want to do is we want to integrate over all values of time to figure out what it is. The integral over all time of the magnitude of x of t dt. Well, let's just look at it graphically. I love to think graphically, and I hope I can get you to start thinking graphically. If we just look at all of this area here, we see this area, but this area is repeated an infinite amount of time. So the total area here is going to be equal to infinity, isn't it? It's going to have an infinite area. So therefore, this is not finite energy. And so we have signals which are in this class and signals which are not inside this class. If you're a mathematician, by the way, and you're into measure theory, and we're not going to get into measure theory here, but if you are into measure theory and it turns out that your signal is Lebesgue measurable, And if it's Lebesgue measurable and it has finite energy, it's said to be in the class of L2 systems. This is L2 signals. This is a very, very important class of systems because it establishes the foundation of all Hilbert spaces. You might not have heard of Hilbert spaces, but you will. And it is a wonderful way to think of things. L2 signals are the way to go in Hilbert spaces. And we'll find out this is a very, very useful class of signals. We also have finite area signals. Let's see if I can do better here. The area of a signal is equal to the integral of x of t. I think you can see that if we have a e to the minus t, we have for positive values, we have the same exact problem that we had before, and this area is equal to 1. It's already positive, so we don't have to do any rectification of it. So this is finite energy, right? If it's 0 for negative time. So it's 0 for negative time, and then it shoots up here and then goes down. That has an area of 1. On the other hand, if we use the same example as we did before with the cosine, and we do a full wave rectification of the cosine, we get something like this. It's almost like the square, except we have these cusps here instead of, man, I didn't do a very good job there. We have these cusps instead of smooth results that we had in the cosine squared. But we have the same problem as before. We have this area plus this area plus this area. This goes on to infinity. And this is not finite area. This is not finite area. It's infinite area. This one is finite area. So you can see finite area signals are important. Again, if you do a Lebesgue measure and you get into measure theory, this is a class of L1. So a signal with finite area, which is Lebesgue measurable, is called L1. If you've never heard of Lebesgue measurable, don't worry about it. You won't hear it again in this class. But this is just a tease in case you are a mathematician and you do like things in measure theory. Bounded signals. This is also very important area. Boy, I don't even know what happened there. Let me start again. This is very simple. You have an x of t, and you have an upper bound, which is c. You have a lower bound, which is minus c, and these are your intervals. And as long as your signal lies between these two bounds, you have a bounded signal. Pretty simple, huh? So a bounded signal is one which lies between minus c and c, and as long as c is finite, that's fine. So if we have something like, where'd my cursor go? If we have something like e to the minus t times a unit step, we know that that's bounded. In fact, the bound here is between what, 1 and minus 1. Should be a 1 down here. So that's bounded. And we have also the case of a cosine. And finally, the cosine is in the class because the cosine also lies between minus 1 and 1. So both of these are bounded signals, relatively simple. So that's kind of cool. So both of these are bounded. There are signals which are not bounded. Let me give you an example of one. ln, by the way, is my notation for the natural log. So it's equal to the minus the natural log of t. If you were to plot this and only over the interval from 0 to 1, and it's going to be 0 elsewhere, you know that this kind of goes down like this. It comes down here and it hits 0 at 1, since the log of 1 is always 0. And at the origin, it goes to infinity. So this certainly is not bounded. What is interesting about this, though, is that it does have finite area. So here's an example of a signal which is not bounded, but it has finite area. How do you know this? You can do a couple of things. Number one, you can integrate and go to a place and figure out the integration. The way that I like to look at it is if you turn this logarithm on its side, and look at its inverse, this turns out to be e to the minus t. Can you see that? Let me try to draw that a little bit better. If you take the logarithm and you put it on its side, you see how I flipped it around? Clearly this area is equal to this area, and if you put it on its side, this is minus log of t, then this turns out to be e to the minus t, so it has a finite area. So this is just the fancy way that I did it. If you don't follow it, you can go and you can integrate from 0 to 1 of minus log of t and get what you want. So this is an example of a signal which is not bounded. Not bounded, but its area is less than infinity. It has finite area, but it's not bounded. Very interesting result. I think maybe, how are you guys holding out? Have you guys ever heard of band limited signals? Okay, I see a couple of nods one way and a couple of nods the other way. I think we're going to wait for band limited signals until we get into the definition of the Fourier transform later on. I think it's more easy to talk about. There's analytic signals. These are fascinating because they have a lot of fascinating results. But everybody remembers the idea of a Taylor series. If you can expand something in a Taylor series around a point, and this point is phi, and this converges everywhere for no matter what value of phi that you use, finite value, it's said to be analytic everywhere. These have some important properties. We won't dwell on them. We probably won't see this concept again, but I think it's important that we mention it because we do talk about analytic signals occasionally. Now, causal signals, this will be the last thing that we talk about. Okay, so take a deep breath and here we go. A causal signal is one which is identically 0 for negative argument. So anytime you have a causal signal, x of t, for whatever it is for positive time, I don't care, but it has to be 0 for negative time. Now, why do they call these causal signals? It goes back to systems. Remember, if you have a zero memory system, what do I mean by zero memory? I mean like a RLC circuit, but if there's no memory, there's no charge on the capacitors initially, there's no current running through the inductors. And so therefore, for a zero memory system, if you have an input of 0, if you have an input of 0, you have an output of 0. Because nothing's there to stimulate the system. So here's the problem. If you have a zero memory system, and you put in, say, at time is equal to 0, you put in, I don't know, some sort of function, maybe an impulse, doesn't matter what it is. If this is a temporal system, you know that your output, this is your input, you know that your output cannot start before time is equal to 0. You can't have an output before time is equal to 0. Why is that? Because if you had an output before time is equal to 0, it would be anticipating the input. The output for negative time would say, here comes the signal, here comes the signal, I'm going to give a response. Oh, there's the signal. No, you can't do that. You have to wait until the stimulus happens before you get a response. So if you put in any result here, you're going to have a signal which is 0 for negative time. So these are sometimes referred to as causal signals or causal systems. You can't have a response before you have an input. Therefore, if you remember the impulse response, if you have an impulse response, let me do it over here. If you have a 0 memory system and you put in an impulse, remember the impulse response of characterizing linear systems? If you put in an impulse at time is equal to 0, you better not have an output before time is equal to 0. Before you apply the input, you better not have a response. So therefore, these are said to be causal systems because that's the case. And we borrow from this idea to define what we mean by a causal signal. A causal signal can be an impulse response for a causal system. It has to be 0 for negative time. And this is really important. But the interesting thing is that this is only applicable to time systems. If you were to look at spatial systems, there's no concept of causality there. And we're not going to talk about space, but imagine, for example, that you have a system, and this is maybe, oh man, I'm terrible here. Let me do this some more here. Let's say you have a signal and you have a lens here and you have an output. So this is an imaging system. And the imaging is such that here is the input as a function of, well, I'm going to make it a function of t, even though t is measured in distance. But the interesting thing is that if you have a impulse at 0, what does that impulse mean? That means you have a point of light. And all your ideas of linear systems, by the way, apply to optics. It's really fascinating. If you have a point of light, does it make sense that your output image can only be on one side of the plane? No, it's totally stupid. Your image is going to cover the entire plane, or at least negative and positive response. So the concept of causality only applies when your variable that you're talking about is temporal. And that's pretty rich, and because of that, you can do some amazing things with optical systems that you can't do with regular systems. Let's see. I did this before accidentally. Let's see if I can do it again on purpose. No, I can't do it again on purpose. Okay, so let me try this then. I'll just make a new slide here. Okay, for those of you who have had systems theory before, let's talk about a low-pass filter. What is the frequency response of a low-pass filter? The frequency response of a low-pass filter lets in signals only on a specific band, minus B to B. Is that okay? Do you remember what the frequency or what the impulse response is? What's the inverse Fourier transform of a rectangle? Anybody know?
Sync, isn't it?
Yeah, it's a sync. So h of t is a sync, a sine x over x sort of function. So here's the problem that you have if you're going to design a circuit that's a low-pass filter. What you want is you want to get a signal, which if you put in a delta function, you want your frequency response to be h of t, right? But this is a time is equal to 0. This is a time is equal to 0. But you can never get this h of t. Why is that? Because the impulse, the sync, occurs before time is equal to 0. So your impulse response would be saying, here comes the input, here comes the input. Oh, there's the input, right? The input occurs over here. There's the input, and now I can trail off. So it would be anticipating the input, but it can't do that since it doesn't have zero memory. So what do people do? They say, well, you know what I'm going to do is I'm going to try to get myself a impulse response maybe that looks like this. Maybe I can shift it, because shifting a little bit is okay. It just delays my output a little bit. And I'm going to make this my causal system. Does that make sense? It's still going to be 0 for negative time, because you're stuck with that if you have a real signal. But your signal itself still has to be 0 for negative time. And that's a problem, because no matter what you do, there's going to be parts of this sine x over x, this impulse response, that still aren't realized. So what do? This is the area, if you've ever taken a course in DFT where you do Hamming and Hanning filters and things of that sort, it's a trade-off of what you do to this causal response that you're stuck with and this zero response that you're stuck with here, and how you do the trade-offs to get different possible low-pass filters. So if you've had those courses in DFT, Hanning and filters and Hamming filters, it's all because of the causality. But the interesting point is that if you're dealing with a spatial system, you don't have to worry about that. It's really kind of cool. We'll be talking more about that probably next time. So next time we'll start with something easy. We're going to get back to something easy. If you didn't totally understand about the causality, don't worry. I'm sorry, the design of the low pass filter. Don't worry. We're going to be hitting stuff to bring you up to speed here very soon. We're next going to be talking about even and odd signals. You don't think this is a big deal, but it turns out to be a very, very big deal. And we'll talk about that next time. So with that, I guess I want to conclude things. Are there any questions at all that anybody has? So I was very, yes, go ahead.
I just said no, sir. I don't have any questions.
Okay, good. Okay. Let me ask you this, because all of you have a different background. And what I'd like you to tell me on a scale of 1 to 10, how familiar is this material to you at this point on a scale of 1 to 10? Let's start off with Justin. What do you think?
I would say probably about a 7.
7. Okay, thank you. Chris?
I'd say 7 or 8. 7
or 8. Okay, David?
Yeah. Let's see. Maybe. 6 or 7.
Okay. By the way, if you give me a low number, that's okay, because I know all of you don't have the background in electrical engineering. it won't make me think less of you. Okay, Adam?
Yeah, probably a 6 or 7. Just need to dust off the cobwebs.
Yes, exactly. That's hopefully what you're going to do as we get here. So, Aiden?
Yeah, I'd say probably a 6, because I did take a class about this kind of topic. Obviously, it wasn't an undergraduate class, and it was an electrical engineering class. But I'd say probably a 6. It's kind of hard to say, but it's all familiar for sure. I just definitely don't remember a lot of it. But
Okay.
it's all very familiar to me.
Okay. Well, thank you very much. This will help me prune the class, if you will, a little bit. Okay. With that, I am going to stop sharing so we can see everybody. And I guess we'll see you next time.
Thank you.